All right, so announcements wide, Austin asked, how do I tell if I can use a different platform for lab than is posted? The answer is just ask. As long as you can extract the fundamental principles of whatever it is. So if you look at lab one, you see the fundamental questions I'm looking for. I'm looking for how far does it go? How long does it take for a piece of data to go from A to B? How does the reliability? I need you to sort of have it break down in loose packets. And I don't really care what platform you do it on. I think the simpler the platform, the easier it is to do the lab because you can see things inside. But again, if you want to learn a Raspberry Pi or I don't care, or a Silicon Labs device, go for it. Okay. Okay, so if I were to summarize, okay, share screen. Oh, first start with questions. Any questions? No. Okay, so once I start sharing screen, I'll stop seeing your faces. So that means you gotta unmute yourself, start talking. Yeah, so I do believe it is recording, and so you'll see the lecture from last week. Should it be up on your canvas? Okay, share screen. Oh, okay. So if I were to summarize, where to go here? If I were to summarize all of last time's lecture, how would you have summarized Thursday's lecture?
The labs are open-ended.
Okay, yeah. So the first part of the first part of lecture was to show you what was in the class and give you some examples of how the labs will work. And yes, I did intend something completely open-ended. As long as you learn fundamental principles of each of the 3 or so platforms we're going to study in detail, and then one more. I don't care what, it's open-ended. Okay, there's no right answer. What else did we learn on
Thursday? Growth is going to be huge.
Yeah. It's huge. Okay. And those are the 2 things that I had in mind. I don't know if there was anything else that happened intentionally. And so a couple more slides here in 1.2. Again, I'm following first 10 chapters or so in the Leah book. Okay. And so the next 5 or 6 slides are looking at applications, application areas, like in this one here, manufacturing. Okay, so we're talking about robots, we're talking about assembly lines, we're talking about building things, airplanes and cars and computers, all that. And so where IoT obviously fits in is a whole bunch of sensors, either for efficiency or safety or energy. Yeah, you will see the workplace of the future. Well, when I was let's see, when I was in middle school, my thought was I'd grow up and work I'd be a machinist, and I'd work in the factory because that's what everybody did. And you look around, and all of the older generation, none of them had 5 fingers. None of them could hear. 50 years ago, the workplace was very dangerous. One of the things that can happen in IoT is making it safer and more efficient. Okay, so you'll see the workmen wearing instrumented up to look for dangerous sound, pressure, temperature, gases, light, whatever. Okay.
I can't see you being a machinist, sir.
Oh, no, you can't. No. Oh, jeez. I thought I was going to go. Okay. And I thought I was going to go into the Navy and do my 4 years on a submarine. Yeah. You can't see me a machinist. But that's all everybody did. That's what people did. They drank their sorrows together. And so, yeah, my sister grabbed me by the scruff of the neck and said, "Hey, do your homework. You don't want that." So, yeah, and it's funny seeing my whatever. Yeah, when you're little, what do? You just do what everyone else did. Okay. All right. So lots of connected devices. Okay. And so everyone every one of these things sort of has an optimization metric. Okay. And down in the corner here has to be effective. You have to produce product and you have to make profit. Okay, so they're very profit generated, which is why the workplace was so dangerous. Okay, and now this is the one everybody thinks about when they think about IoT, is all the cool stuff we can go buy at the mall, right, or on the internet. Yeah, hundreds of computers inside your home. Yeah, we will get to the point where we will wear or have connected to us. Yeah, it's yeah, one of my cats had to go on a special diet, and the vet wanted to sell us one of these feeders, and the cat would stick its head in the bowl, and if we had the right RFID tag, the bowl would open, and if it didn't, it wouldn't. Obviously I didn't buy it. It was too expensive. So it was much easier for me just to feed all the cats the special diet. Yeah, it's this consumer base won't read the data sheets. Okay, and so a lot of these applications have to be intuitive. In other words, they have to be sort of self-operating. And so, yeah, one of the professors who passed away thought that, you've got to be able to, I don't know how many of your smart devices you have to unplug and move the battery to update, but he was very much into consumer devices that would fix themselves when they break, and they would just work.
Question.
Yeah.
Will we cover the FCC in any of this, like the different, how you get
I don't know. Boy.
because all of these transmit devices need to go through.
Yeah, I think there's some stuff in the book on the protocols that each one arrives in. I remember seeing the frequencies that some things are, but I don't think we're going to propose new ones that need to be passed. And it's got to be fun. All right. Okay. So this was an interesting one. When I read it in the book, I didn't realize that this was a whole avenue for IoT, and that is at the shopping mall. Okay. And so you obviously that advertisement is targeted, but how do you fit IoT? That targeted advertising works. Okay, that clearly that's Google and Facebook and all those things are making billions of dollars because of targeted advertising. But how do you make IoT targeted? And that is figure out if you have a store, if you can figure out who your customers are, either by logging onto their watch or their cell phone, or putting putting sensors at your racks and seeing where people are, right? So if you were arranging your store and you could count customers and where they are, obviously they count what they're buying, but you could sense where people are going, and then move that merchandise up closer to the front. Okay. Um, yeah, you know that if you try to walk out of a fancy store without buying it, the alarm goes off. And so, uh, it's anyway, it's interesting. Um, the insurance companies have lots of interest in mitigating risk. And so, yeah, you want OnStar in your car so that your insurance company can figure out when stuff is uh, when stuff is lost. Here's my scary sign. I know the world is lost when I walk into the mall and the sign says, "Welcome, John. Today I know you like red. And so here are all the red things for you to buy." Okay. Yeah, let's see. You know that when you go to a fancy museum, you can have a tailored experience that interacts with stuff. So some of the interesting sort of optimization functions are psychology and the process of what makes us buy and what makes us happy, and again, profit driven. This is probably the place where I have the most experience measuring crap. So whether you can deliver patient care where the patient is. Yeah, my cousin wore a monitor. He was diabetic, and so when he either fainted or was about to faint, various alarms would go off and the ambulance would show up, and that allowed him to stay out of the hospital. You'll see an example in the next slide of where IoT could be used for drug research. Basically, we're going to put instruments inside of laboratory, rats and mice, and study drugs. Yeah, my Fitbit always wants me to turn on the fancy features to predict or prevent healthcare. Yeah, anytime you can get people to stay home when they really can't take care of themselves would be a win, because it is better for the patient, it is cheaper, it is more effective. A lot of money happens a lot of money is transpired. If you watch how it is the healthcare funds itself, by the way, you will see it's basically supplies. The hospital equipment is expensive, and the supplies are assets that make them money. And so if they can control their assets, not just drugs are an asset, which need to be tracked, but as you know, with all this COVID crap, there's a lot of remote medicine going on, and that's probably one of the winners of this pandemic, is the infrastructure for remote medicine. We've had fall detectors to let the people know that they've fallen. Okay. So what are some of the optimization functions? It has to work, because as I tell my 319K kids, if your software has bugs, people die. The whole HIPAA thing, we can't just let some of this stuff is HIPAA, is secure. I mean, it's private, and you got to watch who owns it and where it goes. Yeah, one of the things about this whole platform is you line up 100 people and every one of them's different. I don't care. And I'm not talking about size or color or what language you speak, but physiologically, every human is different than the other ones. So testing is a huge problem, and safety in this, at least in this country, in terms of regulations. So healthcare. You watch the news, I suppose, with the automatic, with the, with the automatic, the self-driving trucks. But even before they were self-driving, you clearly, in order to optimize your transportation, you had to know where every one of your trucks are, what's on the truck, where it is, where it's stuck. Yeah, the same thing with airlines and rail. Where all those things are have to be known, and that allows you to track. You want to, every one of your devices needs to be somehow monitored so that you repair it before it breaks down. Because if a truck breaks down on the highway, it's very expensive. But if you repair it 75% into its life, that is the good way. I don't know. It's I'm 66 years old. I have no idea how they get blueberries from South America to the United States, and they still taste okay. Yeah, I don't know where apples come from in the middle of the summer, because I know apples don't grow in the summer. Yeah, so there's a whole industry for transporting and storing and whatever stuff, so it shows up fresh. You could have on a single truck hundreds of sensors. You could have the trucks talking to other trucks. Here's an interesting one that I hear from my machinist cousins, and that is one, just like in the hospital, one of the assets in all of these industries are the tools. I don't know if you've ever had somebody go into your workshop and borrow your tools, but it's annoying. And so I imagine the world of the future will have embedded devices inside the expensive tools, so that the company knows where they are, when they need to be replaced, and not just a camera at the door to keep people from stealing it, but more, it's on the floor here somewhere. Where is it? Okay. An interesting, agriculture is a fun IoT because of how far it is from each other. It's the opposite of the city one, which we'll do in a second, and that is, how do you optimize energy, water, nitrogen, to improve the safety and the quality and the production of agriculture. So again, a lot of sensors, a lot of interaction, a lot of sort of remote measurements, central decisions, I guess is the way, Now, obviously, all of these industries are kind of connected together. I mean, agriculture has a transportation component. Yeah, I don't know if they'll ever make robots to replace, that pick grapes. I don't know. But if they do, they're probably connected wirelessly to some central controller. The environmental trackers are remote sensing, central for earthquakes and tornadoes and hurricanes and that kind of thing. All right, remote. Um, yeah, energy. Yeah, one of the surprising things that that I got when I first became a professor way back in the 80s, and that is oil companies, energy companies like Schlumberger come in and hire electrical engineers at a great rate. And I go, what's up with that? And so even in the 80s, they were measuring everything. So they'd have thousands of sensors, and now they're connected via wirelessly. Um, yeah, here's another sort of surprising thing. My first IoT project, I didn't actually do anything, I just consulted on it, was one oil company who goes, one energy company who will go nameless, wanted to go onto the property of a second energy company, and without actually intrusive to their device, they wanted to dig holes and embed measurements in their competitors to know how much energy was flowing down the pipe and in what direction. And so, yeah, and it was remote, right? And so they were spying on each other, okay? I don't know if they actually did it or not, because I didn't want the ethics of it. I didn't seem like, even though they convinced me it was legal and it was on public land and whatever, it just didn't seem right to me, so I didn't do that. But yeah, charging cars, making it so it's such that your electric cars get charged at night when people aren't using their air conditioners, or yeah, and again, energy has to be fast, okay, because when one grid goes down, yeah, you got to switch in the other one. So we'll got a slide on real time in a moment, but energy. Cities, this is one that I'm glad I'm not in, because the regulations are probably huge. But how do you control pollution? Yeah, now I don't know if this is true, but can you actually control the weather? Okay, so maybe in the future you'll be able to, but microclimate means block the block. So because of the different absorptions of solar energy on different things, yeah, it's amazing. You go into Houston and you walk down a regular street and it's hot and humid, and you walk onto the Rice campus. I don't know if you've ever been onto the Rice campus, middle of downtown Houston, and boom, it's beautiful. It's the temperature's lower, the humidity's better. That's because they planted a lot of trees and grass, I guess. And, I don't know what they do, but it's, yeah, the pollution is less. I don't know on the Rice campus. I don't know how they did it. Yeah, you have all, traffic lights and cameras, and yeah, in the big cities, it's actually a problem to remove snow. And so, because you can't just push it aside because it's a city, you got to move it. But where it is and where it went is a management system that could have IoT in it. Parking lots are fun. I don't, if you've ever seen one of those parking lots where you drive up and it tells you where to park. You reserve your parking space and that's your spot. Yeah, one of the applications for when we get to the NF, near field stuff, the IoT devices that have no batteries in them, right? They're batteryless, and you charge them up with the electric field. We're going to put them everywhere, I guess. So you drive your city vehicle truck over top the bridge, it activates all the sensors, and it collects data on the sensors. All right, cameras. Oh yeah, cameras. It's a little scary to think about, where someone it was actually a long time ago, so it may not be good anymore. Created a map of New York City of where how could you get from A to B without your picture being taken? I'm not sure you can do that anymore. There's so many cameras. I don't personally know how this works because all of this stuff's obviously not in the public domain. But you know, if you just watch the news, you know the drones are out there. You can just sort of estimate and sort of guess that the hardest thing. I was been watching a Netflix thing on Rome, on the Roman Empire, and that is the reason the Roman Empire was so successful was logistics. Okay, and so from a military standpoint, where's your stuff? Where are your people? Where are your supplies? Where are your backups? Where it is. Yeah, I just got a couple of funny stories. Well, not funny, but stories about government. I was on some panel trying to talk a bunch of generals and admirals and stuff for a new way to do military vehicles. And, it had to do with tires and gearboxes. And I don't know why I was there because I had no skills. But one of the things that they alluded to is you take a device, a whatever, and it has to withstand a 50 caliber shot. So if you've got a printed circuit board running your system, after it's hit with a 50 caliber gunshot, it still has to work. And so reliability is a big deal for them. Redundancy. A lot of this stuff is carried by soldiers, so it has to be lightweight and small. There's a lot of politics, bureaucracy in this area, and so you see how they make decisions, and sometimes not. It's also in the medical domain. Yeah, our most successful medical what's the right word? The medical grants, NIH grants, is when the PI went to Washington and knocked on their door and smiled at them. So there's a lot of handshaking and a lot of networking in this field because decisions are made by humans. So work up your people skills, I guess. This is chapter 1, big impact. Virtually everywhere. And so when it goes to the test and I go, what is an IoT device? It's got a computer in it. It has some sort of logical connection. And again, this is Leah's definition. And then it has a physical connection and it's not a laptop or a cell phone. Okay. Yeah, sure. Chapter 1. Chapter 2. Okay, so this other third PowerPoint in here was just to give you a sense of what I know and what I don't know in terms of what my experience in this field are, and there's a couple of them that have IoT implications. So these are just some projects that I've worked on in the past. The first one is for drug. It's for okay. Okay. Hold on. I gotta change the order of this. Bring this one front. Bring front. View. Sorry, you can't see it all. Bring front. Bring to front. Okay. For drug development and drug testing. So even if it's not a heart drug, the companies have to test to see whether their drug affects cardiac function. And so we wanted to develop implants that would sit, that would be surgically implanted in the laboratory animals. It obviously had to work. Power was a big problem. They wanted it to last 5 months. Size is a problem because, the rats have to carry it around. And if it's too big, the rats get all mad and start eating it out of themselves. Your connectivity, the rats walk around the cage. It's got to stay inside the, it's got to not be, dangerous. And obviously it has to work. But we're measuring heart volume. And here's one of the first ones we developed. You see, it was about a 1/2 inch square. And we'll talk about the physics of how this works when we get to RFID. But the red, what you can see on the red side of this PCB is a coil. And that coil absorbs electromagnetic energy. We'll show you some of the basic circuits of this when we get to RFID, but basically it's going to absorb energy, convert that to a voltage and current to run the microprocessor. The big chip's the microcontroller, and all the other chips are basically analog chips to control the system. That particular thing didn't actually work. And about the same time, the world started making these. So our second version was with an existing technology based on an MSP430. And again, it's got the same sort of physics. You got the base station over here on the left, which you can see is hooked up to a USB port, and that delivers power. And as long as this set of coils is somewhere approximate to that set of coils, you can absorb power. This thing turns on, and then it turns out all you got to do is detune that coil, and the capacitance on this coil here, the capacitive load on this coil here will be measurable on the coil over there, and in that way you can send data in both directions. But this is one of the lab 4. This one on the bottom is one of the lab 4. So how did we, this is a medical device. It's pretty far into the adoption phase. Okay, it's got a RF430 in it. It runs at a pretty low voltage. Okay, running around 1.5 volts. Again, completely passive. And the coil absorbs, this one's a little bigger than the other one, absorbs energy, and then the same coil is also used for communication. And so the rat's in a cage. You put the activation coil down here near the water dish, and then when the rat goes to get water, the coils align, and you can measure its heart function. Is this an IoT device? Obviously, we're not connecting up to the internet. Okay, so technically speaking, according to Leah, this is not an IoT device, but it's certainly a thing, and it's certainly wireless. But the way in which the system will be used is you've got hundreds of rats and hundreds of cages, and each one has the implant in it, and now you need another protocol for communicating to a monitoring station. This still is probably not internet, because this is private data. You wouldn't want your competitors hacking into this, but nevertheless, this might be, you might have drug testing plants in Ohio and other ones in Boston, and now you're connected up via the internet. So this part here we haven't done yet. It's just this part up here that's been done. So that was a rat implant. Um, yeah. There's a second one that I've worked on. Again, this one also is pretty far along in terms of becoming a medical device. This one actually involves in patients. And the medical problem here is an unconscious patient in an ambulance might have embedded medical devices, nerve stimulators, pacemakers, glucose monitors. You know, you might have embedded devices in you, and if you're unconscious or forgetful, you don't know what it is. I mean, the strangers, the doctors and in the ambulance technicians don't know what it is, and the way in which the standard of care is they have to wait until you end up in the emergency room. You have to bring in the portable X-ray. You put the patient in the portable X-ray and you X-ray them and go, oh yeah, that's a Medtronic, or no, that's a, you know, that's a St. Jude, or that's a Biotronic. That's a, yeah, there's you know, that's just something, you know. So but that process could take a half hour to wheel in, to get an X-ray, wheel in, figure out what kind it is, and then you can start treatment. And so this is a device that would end up in the ambulance itself, and they would just scan the patient, and it would tell you all the devices you have, and then alert the staff in the ER, and the ER alerts the staff at Medtronic. So actually, once these patients are in the emergency room, the Medtronic representative is in the loop about how to diagnose and how to treat the patient. And so if you can shorten that loop, that's the idea here. So the reason why, you know, it's you'll see why it's an IoT device. The first, like the rats, the first communication is local and using a coil. Okay, so there's a coil device that's passed over the patient, and communication. Now, it doesn't have to pass energy because the pacemakers have their own batteries, but it does communicate with the device to say, hello, and then you can, and then you ask them what, you know, and then they respond, hola, and you know that's a Spanish one. Or if you go, hello, and they go, you know, ciao, you know, it's Portuguese, right? So each of the pacemakers have a certain protocol that that they communicate with, and you sort of, you know, you speak the international language of hope, right? And they start speaking in their own language, and you figure out who they are. A very fun, sort of scary problem is, you know, this was an interesting interesting experimental process, because as you might imagine, all of these protocols are proprietary, and you know, when we first started this, I ended up with like 50, 100 pacemakers, and I just warn you, this is you know, these communications are not very secure, because just a regular guy with a coil, I just had a coil like right here, and I could basically hack into all of those codes. You know, there was one that was really hard, and we went to the manufacturer, and I said, well, try this, and it doesn't work. And the guy smiled at me. He says, you are very close. And so we tweaked it a little bit more and got the last one to work. But it basically has one wireless link that communicates between the pacemaker or the device and the machine. Again, it's a yeah. Okay, so let me. Okay, and I'll just let it. Yeah, that's not it. Okay. And then again, that is a proprietary protocol a communication. And then because one of the features that we had in mind is if we could somehow in a what's the right word, in a safe and protected way, embed each of the pacemakers, each of the pacemaker companies' intellectual property into these little boxes here, and just connect our universal programmer to a secure internet production. And now, if this is a Medtronic pacemaker, and this is actual Medtronic code, that is some sort of object code kind of thing that we can't see, and then here's a bridge to the Medtronic programmer that you could have. Remember I said, when someone with a Medtronic pacemaker shows up in the emergency room, someone at Medtronic is on the phone talking to the ER doctor. But if you could connect the Medtronic rep directly through to the patient, the doctor's still there. This is our vision. And so this is clearly an IoT device because this is the internet right here, 92. And again, we're at this front end stage. Yeah, we've got patents all over. Yeah. This is a figure from this is a figure from Leah book, and they have an example here in chapter 1 of a wearable device. And let me summarize this and all the other ones, and that is these things can get complicated, and they have a number of layers. Okay, so it's not one system necessarily, but it's a connection of systems. So for instance, for this wearable device, you have the physical sensors attached to the patient and the battery or whatever in your watch, and it's connected across, say, a Bluetooth channel to a listening device, maybe your cell phone. Okay, and the word edge computer just means it's out there in the rain. Okay, so if it's raining outside, the edge things, whether it be the physical sensors or the computational stage, is going to get wet. So for instance, when my Fitbit analyzes my sleep pattern, it's not doing it in the watch, it's doing it in the phone. Okay, and if my phone is then connected to the cloud, now I have all of my private stuff available for everyone to see in the Fitbit cloud setting. Okay, so this is sort of a layered approach to the device. Okay, so I should have done it this way. Sorry. Now you can actually see the photos. I was going to ask if you could see it, and the answer was you couldn't. But I already did this. There are some devices out there that advertise that can measure your EKG from your wrist. Yeah, I'd be careful. I've seen some devices say they measure blood pressure, but they're just guessing. So you got to be careful in this field. On the other hand, one of the Bluetooth labs could be a fitness device. One of the Bluetooth example project platforms is Creative Fitness device. Okay, so I should have shown you that. Yerubali offered to teach the MQTT lecture, so we'll have a later in the semester. We'll have a guest lecture to teach you MTQQ, which is basically a protocol on top of TCP that allows you to send secure messages. And then this is actually a place for which I don't really have any experience in the cloud. But how do you handle hundreds or thousands of patients? How do you deal with security? How do you allow the doctors and nurses to get at things? Yeah, an interesting billing flaw is with this COVID stuff, everything doesn't work at the same rate as it used to. And so the air conditioner guy came and was fixing my air conditioner, and he presented me a bill. I wrote him a check, and however it is they did their billing had a step due to COVID that was delayed by a couple of days. And so the guys in the central office, you notice that the repairman was at the house, and whatever 7 days later, they hadn't been paid yet. And obviously I gave the guy a check. He's probably sitting in his truck, working at home, not going to the office. And whatever, ended up with one of the nasty letters from the collection agency saying, well, you owe this bill. And, yeah, fine. Whatever. So billing, yeah, I hate it. Okay, so yeah, so that's yeah, there we go. That's lots of examples of IoT things. Are make sure you identify who your, not stakeholders, sorry, typo, sorry, stakeholders, not stakeholders, stake, I can't spell that. How do you spell steak? Oh, I don't even know, steak, like that? Is that the right way to spell steak? Oopsies, or do I need the internet? Whoever it is that you're, you know who I mean, your customers. Yeah, identify your constraints, because you can spend a lot of money solving a problem they don't care about. So yeah, and they will care about some things and they will not care about other things. Yeah, testing is important because everything's different. All right, questions on that one? All right, boring. Okay, so all right, so now we're going to talk about. Now I'm into chapter 2, architecture. There's a, yeah, it's, chapter 2 is kind of boring. You could summarize all of chapter 2, and that is a bunch of pieces and networks, just like the examples we just did. Often it's not two things being connected, but hundreds of things being connected, and connected in different ways. Some of which you control and some of which you don't do. Chapter 2 outlines the LEA book in terms of sensing and power, communication, and some edge computing. It also talks about machine learning and security. Those aren't things that we'll probably get to, but I still think the book was reasonable. Today we're going to do Metcalfe's law and Beckstrom's law, and the definition of real time. All right, so just like the last slide, the architecture is devices and interconnection of devices. So you've got sensors and actuators, you've got the personal area network is you and your stuff, and it's obviously wireless. The local area network is bigger and has stuff that's not necessarily just your stuff. And then once we get on the internet, we have the routers and the gateways, and the wide area networks are worldwide. Okay, so when you talk about a local area network, you're talking about a building that has people sharing stuff. I mean, sharing whereas a personal area network, like labs 1 and 2, you control both sides, both the client and the server. Whereas a local area network may be like a Wi-Fi hotspot. And the wide area network is the whole internet. Okay. Oops. Yeah, so this one I broke up, and so I remember this one. So interesting, he drew the other picture the other way around and drew the cloud at the bottom. This one he drew at the top, but you know, how do you get data into your system? Either HTTP. We're gonna the Wi-Fi lab. One of the options for the Wi-Fi lab is if this, then that, which is an aggregator to ingest information. Again, security is important. You're gonna have to take some other class. All I know is it's important, and I don't want my stuff to be lost. There are faculty out here that do storage. So again, not something that I'm there, and I'm not a machine learning. So there's very little at this top layer that we're going to do in this class, but there is one. And then the middle layer, again, the wide area network, that's the internet, okay? That's the things that go long distance, whether that be the broadband backbone of the internet or cellular. And then the personal area or local area network layers. This is where we're going to sit mostly in this class. Now I have done some Ethernet, so I don't know if I get near the end and I run out of stuff to talk about, I'll add Ethernet. But we're going to do Bluetooth. We're going to do Bluetooth is sort of here in this local area network, personal area network, and Wi-Fi, and then Zigbee is an example of the sub-gigahertz range. That's our first lab. So yeah, we're gonna introduce the far edge. Okay, so again, edge is the definition of edge is it gets wet when it rains. Okay, I guess far edge means it actually touches the device, the sensors and actuators. All right, so here's the first of the two formulas. Metcalf, as you know, has come back as a faculty member here. His role, as far as I can tell, is entrepreneurship. He doesn't teach classes, although he is available for consulting if you want to reach out to him. You know, a guy who put together Ethernet way back in the day. But this is a really old formula when he first started his network stuff, and that is value is nonlinear with the number of nodes. So if you double the number of nodes, you have more value than double the value. However you define value, which I guess is revenue. Okay, so if you, the way this picture shows, the value is the revenue, so the profit would be value minus cost. Now cost, not necessarily true, but in his formula here, doubling the number of nodes doubles the cost. So at some point, a system will be profitable as you increase the number of nodes. Now the problem with Metcalfe's law is obviously if you double the number of nodes, it's not, you know, it actually gets worse. Okay, so some stuff gets degraded as the number of nodes is. The other is the, you know, the levels of service, right? The whole you know, commodity. Are you a first tier or second tier device? Do you you know, when you set a UDP packet, it goes a different way and send a TCP packet. If you're sending packets across your own company provider, you know, it goes at a different speed than if the company's sending packets through their competition. Yeah, nobody knows quite how that works, but you know they're doing it. Obviously, the more nodes you have, the less reliable it will be, and we'll see that in the first lab right away. We'll see that you'll choose a channel to communicate on, and whatever, there'll be 200 channels you can choose from, and depending upon who else is in the air, you can improve your reliability by hopping different channels. And we always got bad people, so if you invite 100 people to your party, one of them's going to be disruptive. So you got to watch out for that. Okay, so that's Metcalfe's law. And then this one is really complicated. This is obviously, I just copy pasted this out of the book, Beckstrom's law. But this formula will get a lot easier if you remove the index. Okay, which one do I want? I want to move the index J. Okay, so J. Oh, it's already done. So if you just ignore the letter J here, because J is the network. So this assuming you have a system of networks. So just ignore J for a moment. And then what they've done is if you go back to Metcalfe's law, the nodes here are the I. Okay, so in this context here, the I is the number of nodes. Now, whether that's physical people or IoT devices, in our case, it's probably IoT devices. Okay, and then the N here is the big N over there. Okay, so the big N number of nodes is the little n over here, and so so the way to okay, so that sets that shows you the relation between the two. Okay, so now let's look at K. Now this is lawyer talk. This is somebody who's defining this problem at such a granular level, right, that they're going to analyze the benefit and cost of every packet. Every single packet is going to be analyzed. And so you send a TCP packet and you go, woohoo, how much, how good is this TCP packet? That's B sub K. Okay. So B sub K is the benefit of a packet being sent on device I on network J. And then C is the cost of sending that packet. So B minus C is profit. Okay. And the cool part of this, if you'd like, is the fact that it does contribute to two of the factors that was described here. And the first is service degradation, and the second is is performance. How long does it take for the packet to get there? Okay, so again, this person must have been an accountant, because he defines the discount rate as an interest, whatever. And so, R is an interest, but the interesting thing in the equation is how it invokes T sub K. That's what you're measuring that in lab 1, okay? Lab 1 is going to measure T sub K, and that's the elapsed time for a transaction K to go from A to B, okay? And so as time transpires, something happens. Okay, so I'm going to go back and look at your faces.
I have a quick question. Can you explain the rate of interest a little more? Like, what is the sense of that? Is that 0 to 1 or
1%, 2%?
So it'll be a percentage?
Yeah, it'll be a percent, because you learned in 9th grade that dimensional analysis, right? So what's the dimension of 1? What are the units of the number 1?
Unitless.
It's unitless. So R has to be unitless. Okay. So it's a rate, like 1%, 5%. And it's in the denominator. So we're going to get to this. All right. So you shall assume that R is positive, right? You're not making money by delaying the packet, right? It doesn't become more profitable to delay the packet. So R is a positive number, 5%, 10%, whatever. And T is a positive number. You've got causal systems. It has to go forward in time. You can't send a packet today and have it show up yesterday. Okay. So T has got to be positive. R will be positive. So what is the effect of time on the profit, B minus C? I just want you to get an intuition of what this equation is, because it's a lot less complicated than it looks. Okay. So B is benefit and C is cost. B minus C is profit. And just assume from
increase time, then you decrease profit.
Yeah, you could okay. Who said that? Like I didn't say it again.
If you increase time, then you decrease profit.
Yeah. So profit decreases the longer it takes. So I mean that's a fancy equation for saying something that's trivial. I mean it's obvious. Okay. Then I don't, know how many of you have had okay, so I have one last thing before we go to the pink box. What is the shape of the profit versus time curve? If T were 0, what would it be? Right, if T sub K were 0 for a particular packet, what would the profit be?
And
Benefit
B minus C.
the cost.
Yeah, B minus.
It would be linear.
No, wait. Okay. Well, I want you to plot profit versus time, and that's definitely not linear, right?
Oh, I think that would be logarithmic.
Okay, now fine. Good guess, but you still don't have the right equation. But we'll get to that in a second. But it's the maximum profit would occur at T equals 0. You with me?
Yeah.
Okay. And the profit decreases as a function of time. Yeah. Okay. So now somebody will now answer, what's the shape of that? What curve is that?
Decreasing exponential.
Exponential. It's a decreasing exponential, right? So if it were in the numerator, that would be minus T, right? Some positive number, to the, so it decreases exponentially. All right, so I've got 3 or 4 slides on the next question. So this is just me polling the audience to see if you know what these terms mean. Have you heard of the term hard real time, firm real time, and soft real time?
Not firm, but the other two.
In an operating system context. So it's okay if you don't know the next 3 slides I'm going to teach it to you. So I just want to poll the audience and see how many of you already know what this means.
Would this be soft real time?
Okay. Whoever said, who said that?
Yeah, I said it.
I can't see who. I is
Corey, I
Corey.
think, talking.
Corey said. Okay, yeah, good answer. Yes, it is soft real time. Okay, so Corey, why is it soft real time? Okay, good.
Well, I'm trying to remember the definition. So hard
All right.
hard real time.
Yes.
Yeah.
He flipped the coin.
Yeah. So if I remember right, hard real time is like there's a deadline
Yeah.
to where you want the packet, and once it's past there's no value. And
Yeah.
this is just a decaying exponential. Firm real time is like once you pass the deadline, the value starts decreasing, and then after a certain point, it drops to 0.
That's it.
And
That's it.
then
Yeah, that's fine.
soft doesn't ever
Yep.
have like a hard drop; it just slowly decays. So.
Yep. Okay, so so that's what Corey just said. Hard real time is a timing constraint. It's completely unacceptable. We will throw it in the trash. People will die. The deadline that can't be missed. Yeah, no packets get lost. All packets show up on time. It's really pretty hard to do. Firm real time is as that T, right? As that T over here, right? So when I ask you on the exam, I'm going to ask you to write Beckham's law for a hard real time system, right? Just telling you. Or I'm going to ask you to write Beckham's law for a firm real time. It's already solved. Okay. In a firm real time, once the time as it elapsed, there will be a cutoff that beyond which the value is 0, but nobody dies. Okay. It's like, once you miss a deadline, that the value of that packet has no more value. But you go, well, I did my best. I got enough packets that I can reconstruct what I'm doing. Okay. So the value is a function of time, basically is a straight line, and then it cuts off to 0. Or as Corey said, you could have a firm real-time system where the value slowly decreases in time, and then it goes to 0. But once it goes to 0, you just go, well, tomorrow's another day. I'll wake up and do my best the next day. Okay. And soft real-time, that's an example of a soft real-time. As time elapsed, the value of that system gets smaller and smaller. Okay, so let's do some more examples. Okay. If you've got a pressure inside of a power plant, once the pressure goes above threshold, you better shut that bad boy down or you're going to have an explosion. Okay. And whatever it is you're doing, that's a hard time constraint, because after you've hit a catastrophic event, then it will the value of the system, not just the value of the data, the value of the system goes to 0. It just exploded. Okay. Multimedia, streaming audio, streaming video as a classic example of firm real time, because if you lose some image packets on your digital television, the screen may flicker a little bit, but nobody's sending it back. You may or may not perceive the audio or visual flicker. An interesting physiologic thing is which of your input nodes has higher bandwidth, your eyes or your ears? In other words, if you were looking at the constraints of a system, and ignore for a moment that images are bigger than sounds. So, but if you were to look at the timing constraint of a video packet versus the timing constraint of an audio packet.
Audio.
Yeah, audio.
Audio.
So this is 10 hertz, and this is 10 kilohertz. Okay. So your ears can hear stuff, we get our piano tuned. The guy brings no electronics at all. He just uses his ears to tune the piano. It's awesome. And then soft real time, when you're buying and selling, if you're trying to profit in a trading system, your profit, if you can buy quicker, earlier, you gain value from that transaction. If somebody gives you a stock tip, not insider trading, that's illegal. But if you see something that you can make a decision on, the quicker you make your decision, the faster you send your system, the more money you can make. This was a big deal when they put in the fibers across the Atlantic, because people could really make money if they could squeeze a few microseconds or milliseconds out of that transmission and get their data quicker than everybody else. So the value is a function. Okay, so here's another. Okay, so now, now I'll put the thing back on again. Okay, where's my bucket here? All right. From an IoT perspective, Can you think of another hard real-time system?
Pacemaker.
What about the pacemaker? Okay, pacemaker. Okay, so whenever you have hard real time, you've got time from the sending of a packet to receiving a packet. Yeah, I want the IoT part to be, the pacemaker itself is real time, yes. So yeah, fine. The sensor to trigger in a pacemaker is clearly the atrial sensor, ventricular trigger. That's hard real time, but it's not really. Okay, you get, that's fine. That's okay. I'll get that. Okay. Don't answer another one until everybody's answered. Don't answer a second one until everyone's answered one. So it behooves you to go first because the easy ones are easy. So I'm
Some sort of,
okay.
for hard real time, some sort of airbag for like a drone or something falling out of the sky.
Again, yeah, airbags are hard real time. Yeah. Okay, fair enough. It's like the pacemaker, sensor to trigger. And the airbag would be an IoT device because it's going to trigger OnStar. 911 is going to get called. So yeah, that's a. I wouldn't say, but let me ask you: was that Jackson who said that?
Yeah, it was Jackson.
Okay, so let me have a follow-up question. Okay, the trigger between the airbag and between the radiator sensor being squished and the airbag going as real time. What about the transmission between the airbag and 911? How would you classify that?
Well, I think your deadline is a heck of a lot longer, but it'd still be hard real time at some point. Just with a really long deadline.
No. Anybody have any other thought? What is the cost if it takes 2 seconds, 3 seconds, 4 seconds, 1 minute, 2 minute, 3 minute? What happens?
The value decrease because
The
people
value decreases. Okay.
Fair enough.
Now, at some point, I guess you want to cut it off, and if it takes 2 weeks, you're dead. Nobody cares. But that may actually be soft.
Okay.
Airbag to 911. Yeah, good.
I guess it could be firm. Just if it was life threatening, or you're going to die in 5 minutes.
Yeah.
Then perhaps at some point the value is pretty low.
There, but you're pointing out the fact that there is a huge continuum, and so that's my case. Someone else want to put something in here?
Wait, if someone's gonna, sorry, go ahead.
For hard real time, maybe like a automated flares on like a drone or something like that. So the missiles targeting a drone, it has to release flares.
Oh yeah, sure, all the
before it.
Defense, sure.
For the airbag to 911, isn't firm real time say like if you miss the deadline, there's nothing harmful about it, but if you die, isn't that
no
harmful?
value? Yeah, no, good answer, Keyshawn. So I would probably, I would
also hard real time at that point,
and make this value go negative. Right. So at some point you're going to die. Right. That's the whole point of calling 911. And I guess once you get dead, you don't become more dead, I guess.
So would it be hard real time?
Let's take it off of this, because I think one of the characteristics of firm is if you miss the deadline, you don't care.
Yeah.
And so
would it
I
be
think
hard as well, or no?
I'm sorry, say it again.
Would it be hard real time? Because if you miss, like you dying, then that's harmful. Or no?
Fair enough. I'm saying that the answer is not necessarily obvious. So when I ask this on an exam, you have to tell me why. Okay.
Oh, I got one.
Somebody.
Oh, all right. Never mind.
Yeah, I'm sorry, Austin. I want to hear from some other people. Anybody else want to put one in?
For soft real time,
you could put like video entertainment systems. Like if there's a lag, quality goes down, but no one really cares.
Yep. 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 Yeah, sort of like a video controller kind of thing. Yep.
Streaming in general can fall under soft real time because if it's like audio or video, our brains can't even really keep up and notice lag unless it's like super long.
Okay, but okay, so what Rita I think the world will categorize streaming as firm.
Oh.
Because thinking about there has to be a decreasing value as a function of time. If you're outputting frames, 30 hertz, 30 hertz video stream, it doesn't matter if I'm going to output this frame, it doesn't matter when I get it in here. Okay, if I receive that frame and this is time, right? It doesn't matter when I receive this time, when I receive this frame. If I receive frame 12 anywhere in here, it has perfect value. But if I receive it over here, then it has no value. Okay, or if I receive it over there, whatever, it has no value. So I'm trying to think of a streaming application where the packet arrival time, the value of a packet decreases in time. I just don't know of one. Now,
I mean, the video game example is pretty good, but that weird category, right?
Yeah.
Like
So, but that is a packet that
Maybe like document sharing.
sharing.
Like
Okay,
Google
where do you want to put
Docs.
it? Yeah, I like it. I like it. Document sharing. Where is that?
I think that would be an example of soft real time. So like having the constant updates, like it doesn't need to be immediate, but
Yeah, but if
value
it's
decreases
the
over
longer,
time.
yeah, the value decreases. Yeah, and it doesn't decrease to zero. Okay. Yeah, it just decreases. Yeah, I like the doc sharing.
So for firm real time and hard real time, after the deadline, do you just throw away the information? Does
Yeah,
not
no.
matter?
With the hard real time, you throw away the system.
Okay.
Yeah, here you throw away the system is discarded. Over here, you're throwing away the data.
All right, so I got one. What about like hospital telemetry? I mean, that's
So you're streaming data from the patient into the nurse's station.
yeah.
Where do you want to put it?
Well, I mean, I wouldn't throw out the system if there'd be backup alarms beeping and things like that. But I would consider it probably a hard real time. But there are redundancies.
Okay, but okay. So let's say your blood pressure, you're doing telemetry on blood pressure. Okay.
How about EKG?
Okay, EEG. Fine. You're doing telemetry on something, and you've got a medical event. What is the cost of it being delayed?
If you flatline?
Yeah, if you flatline, you stop, your heart starts breathing. Okay, so that's hard real time. Yeah, fine. If you stop,
there are redundancies.
Yeah,
So.
Yeah, it can be, yeah. So if patient dies, death. If you have a system for which the consequence of whatever you did wrong is death, then it's hard real time. Yeah.
So like for, I guess on an exam or something, like the justification for hard real time would be if you miss the deadline, the system goes down.
Yeah, the system's broken.
And then in firm real time is if you miss the deadline, you don't care and you throw away the packet. And soft real time is that it just loses value. So that would be the justification that you would accept.
Yeah.
Like, I mean, there seems to be a lot of like blurring here. So
Oh, there's a lot of blurring. Okay, so welcome to the big boy. We're a big boy, big girl room. Okay, yeah. Sorry, a lot of blurring, and the world doesn't necessarily believe in these terms either. Okay, right? So you know, in the book, you know, they didn't mention the Beckstrom's law of soft real time, right? They just defined it. Okay. And it doesn't actually matter what you call it. It matters what you define. And yeah, you got to make money. Okay. Okay. So here, I got one more example. Okay. Austin will know this one because this is the breathing unit. Okay. So this is obviously not an IoT device. Okay. But the red curve is air pressure in a ventilator. Okay. And if you zoom into your eyes right here, okay, so this is measured pressure. Okay, right there, you can see that the pressure goes from flat to negative large slope. Okay, that is the patient trying to breathe right there. And then right here is the patient got the breath. The pressure went up because the patient did the breath. And so there is a delay between the triggering event, which is the patient wanting a breath. And it turns out this gray dot right there is actually the time in which the algorithm detected that the patient wanted a breath. And this is the time, so, right, so that is the time when the algorithm detected the patient wanted a breath, and the red is when the machine, the mechanical part, gave the breath. Okay, so how would you? This is kind of physiologically cool. The patient stopped breathing; it gave up. Patient stopped breathing over there, and the stupid machine gave him a breath because you can't live without breathing. Okay. So is this hard, firm, or real, or soft? Oh, let me tell you what happens.
Categorized as the person?
Let me tell you what, okay, Keyshawn, go ahead and guess.
Is the system of the person?
Yeah, this is a ventilator, right? For people with COVID in the hospital, right? Who can't breathe. And so we're gonna pump air into their lungs. Okay.
So yeah, I guess hard real time, because if the person dies in 2-3 minutes, then it's useless to give them a breath.
Yep. Okay. Or it turns out if you delay a half a second, it's not even 2 minutes. If you delay a half a second, what you're going to do is you're going to explode their lungs. If you give them a breath, if they breathe out, okay, right, and if they breathe in, and then if they breathe in, and then you give them a second breath on top of their breath, you'll explode them like a balloon. So it's actually not even minutes. It's really half a second. Is that if you got to deliver the breath before when the patient wants it. So the doctor, the pulmonary physiologist describes latency, and it's sort of a very tough problem to solve. Is the brain senses hypoxia, low oxygen, and says, I want air, okay? And then either they get air on their own, or the machine gives them air, okay? And it turns out there are two parts of this response. One is completely in the patient. The patient wants a breath. They have to start sucking in air. And so we don't have electrodes in the brain, so we can only tell they want air is when they drop the pressure. So the first knob here is this one. Okay. And it takes a certain amount of time, 80 milliseconds or so, for the patient to pull the pressure down to trigger the device, and then another 80 milliseconds, because it's actually this is actually what the time they're getting air. when there's an inflection point in the pressure, they're getting air. So that it's pumping air at that point. But this figure illustrates, there's something illustrative about hard real time in this figure. You see what it is? Go back to the word hard real time. What does it mean?
If the patient doesn't get a breath in enough time, then the patient dies.
Okay, yeah, but what? Yeah, there's another term. There's another thing, and that is all the time, not just once, or not just it's in the worst case. Hard real time is worst case latency. Okay, so the illustrative part of this curve is it not just in this one, but in that one and that one and that one and that one and that one, and thousands. Okay, and all of them, it had to give breaths. Okay, all right, so that's that. Okay, so
It's not an IoT device, to be fair.
that's not an IoT device. It's just an example of hard real time. Okay, yeah, but yeah, it's what I did last weekend, so you get to see it. Okay, yeah.
Say you missed a breath. Say you skipped a breath and then it came into the next breath. Would it be hard real? Like, would the patient die?
No,
Like, say you skipped one of these spikes.
no, it would not die. If you
So
gave
then
us,
would it be firm real time? Because it's not.
oh, I see, you're
harmful.
lawyering up on me. I get it. Hold on, I'm thinking.
I'm very confused now.
I know, no. The confusion is okay. Is that Keyshawn talking?
Yeah.
Okay, the confusion is on purpose. Okay, there was a method to my confusing it, and that is there is not a line between these three things. They are they're the boundaries between these three things are not distinct. And so, yeah, so you could claim that this is firm. If I miss one, sure. If I miss one and it just skips a breath, it has less value, but I discard it. Yeah, sure. Yeah.
Okay.
I saw you put this on the MOOC course, the update for this. I saw it last week when I was looking at it again. But yeah, so you did this with San Antonio folks as well?
That's right. This is yeah, in Austin, wrote most of this software. So this was a team of about 20 of us. We just got our response from the FDA, and so we're busy rewriting our submission.
Well, it was good to see that someone at UT is actually doing something. We mentioned it in our lab to like, what ideas will we have to help with all this pandemic? And we were all too busy with our own stuff. And so, but it was cool that I actually see someone.
I mentioned it in the first lecture, and that is you guys suffered the brunt. My plan was to actually organize this course, but no, I did this instead, but it's fine. All right, so enough of that. Let's get back to IoT. Yeah, this picture is illustrative of what you already know. What is engineering? What is design? Design is the choosing components and interconnecting them together. And so everything, whether it's mechanical or chemical or electrical or biomedical, is a collection of things and interfaces between those things. It just turns out that IoT has got some cool wireless connections. That's all. It's still an engineering device. This was an interesting thought that Austin and I had yesterday in office hours. And so again, I'll open up the thing so I can see your faces. Where's my doodah here? Where's my faces? Okay. So what is the most important property in choosing a thing? Okay. Whether you're choosing a microcontroller or you're choosing, and I'm not saying choosing between sub-gigahertz and Bluetooth. Okay. I'm talking about, I'm going to use Bluetooth, and now I have to choose Silicon Labs or TI or whatever. I got to, and actually, it turns out Nordic Semiconductor is probably the best Bluetooth manufacturer out there. He said biasly, for the following reason. So if you were to choose a Bluetooth a module, what is the most important factor in your choice of that module?
If there's drivers written for it already?
Yeah, it's all, somebody's already solved the problem for you. Okay, time is up. Okay, I will come back. Yeah, that's the right answer, Keyshawn. All right, so also somebody got to set an alarm. All right, so let me go ahead and stop because it's 11. We'll pick up here. I think I'm almost done with this one. I am going to hang around for questions, but my next official office hour, I think, is tomorrow at 11. Okay, so yeah, I just see my next meeting clinged off, but I'll wait. So I'm going to stop official lecture at this point, and then just answer any questions you have about anything.
Could you go over how to manipulate the equation for like firm real time?
Oh,
like, I guess like if the value, if
sure.
value drops off for firm real time at a certain time, would it be like a conditional statement mathematically?
Yeah, sure. Yeah, sure. Yeah. So I see what you just asked me. How do you solve the, yeah. So, you know, it's you know, the member of the, okay, where's my, just this. Okay, come on, stop.
So could you just do like a piecewise function where it's that function already for t is less than tau and then 0 for t is greater than tau or something like that?
You remember back when you did 313, you had these you know, these u of t functions that were like that.
That was a long time ago.
I know, but okay, sorry. And so if u of 0 is 0, okay? And so we could have, what function is this? Okay, this is 1 and that's 0 and that's 1. What if this is time 0 and that's time 1, what function is this? Come on, 1 minus.
So yeah, it's the
0,
1 minus that t minus tau or what have you.
Right? That's this. So what is this? Right?
The multiplication of those two.
Yeah, multiplication of those two. And Keyshawn, you're allowed to draw it, I guess, if you want. If you want to just say, you know, f of t is this. And then, you know, value.
Oh, we can draw it on the test? Okay, that's all I need. Thank you.
Yeah,
that's good.
But come on, you are engineers, right? You can write functions for this bad boy. Is that what?
Yeah, that answers it. Thank you.
Yeah, fine.
I have a quick follow-up question to that. And for hard real time, would you define it as having the same value or a decreasing with time value before the deadline?
I think either. Okay. Yeah, it may, you know, yeah, it's, yeah, getting back to my ventilator thing, it actually does decrease in value to a certain point and then it becomes catastrophic. Think about an airbag, okay? Think about the airbag. What function would you have in terms of the value of the airbag? Is there any advantage to triggering it faster? Maybe. I don't know.
I don't know. Well, if the person's 5 centimeters from the steering wheel when it happens, you probably get a lot more whiplash.
Well, that's in regard. I mean, that's a different. Yes. Oh, I see. So the value would go down.
Yeah, just because it would probably be best if you were still pressed against the seat in the event of a collision, as opposed to
With an airbag, it probably, again, I'm not having studied that. It's, the point is you want to define what it is and write your value function. All right. And then once you've got your value function written, you can optimize.
Okay.
Yeah.
Cool.
How many lives, it's unfortunate. The insurance company maximizes profit, right? And they only made to maximize profit is to put a value on death, or more precisely, a cost on death. And not to minimize death, but to maximize profit. So, yeah. Anyway, we've officially stopped lecture, and I'm just answering questions. Okay. And I will do better at the time here. Maybe I'll put a clock. I need a clock. That's what I need. Or I'll set my phone to ding. That's what I should do. Yeah. Because when I'm wandering around the room, I could see your faces, right? And the kids start shuffling when it gets close to the end of time, or somebody gets up and goes, right? Yeah, that's a downside of Zoom. I don't necessarily looking at your faces all the time. Any other questions? See, I told you guys would like Keyshawn, right? He wants to know how to solve the question. Yeah, good job, Keyshawn. Keep it up.
That's what I'm here for.
Yeah, no, it's it's what you do. You question everything, right? So, yeah, I won't know the answers to everything, but I appreciate you asking. All right. Well, going once, twice. Okay, so we'll see you on Thursday. Office hours tomorrow at 11 and 7. Okay. So be safe out there.
Hey, Dr. Valvano.
Yep.
I am kind of like the last guy in the lecture one. I am a little overcommitted this semester, but I kind of was wondering if I could still kind of watch the lectures and audit it for when I want to take it fully.
Oh, you're fine. Okay. Yeah. Okay.
Yeah. Hey, how's it going? How you been?
I was looking at, but whose mouth is moving? Okay, fine.
It's moving fast. It's moving. I talk fast.
Okay, so you have my blessing to do whatever you need. If you want to officially drop, send me your EID. I can add you to Canvas.
Okay. You must send it email or through Canvas or?
No, I don't. No, it's email directly is the right way.
Okay.
So.
All right. Hey, I'd like to still do some of the labs, but I got a professor who wants me to take some of those ME classes. You know, those ME classes that they like you to take, right?
It's the same math, right? It's interfaces and things.
Yeah, it's just all system, right? You're breaking it down into modules.
So the only thing I would do is be cognizant of choosing a lab partner if you're really not going to do anything. That's really.
Yeah, no, I would just do it on my own.
Okay. So I don't know. Are you official? You must be in Canvas now. You wouldn't be.
Yeah.
Able to get.
Otherwise, I had to. But they only allow me to take 3 classes, and I think the finances they probably paying for more than 4 classes. So.
All right. So you'll have to send me your EID, and you may want to do it in 2 steps. You actually have the Zoom link for lectures now, by the way. It's the same.
Oh, okay. Link. Same link.
So it's this. If it takes a while to get the.
Yeah, it takes a day normally.
To get it off and back on again, just come back to this same Zoom somewhere.
Oh, cool. I appreciate it.
You can also copy down the office hour links before you uninstall, unregister, right?
Roger that. Now I'd like to, are you doing a demo for the ABUU? Where is it at? Or ABBU? Where's it at right now?
Am I doing a demo? Jeez, obviously it's way past lecture, but geez, demo.
I'd like to see it in person.
Okay, fine. It's if you can get up the elevator in EER.
Yeah.
5.822. There's 2 of them in the window.
Okay, cool. I'll write that down.
Yeah, I don't know if you can get up the elevator, but
I'll crawl.
Okay, so
Tom Cruise it.
Yeah, yeah, fine.
Cool.
Yep. Take care. Anything else? All right, well, take care. We'll see you. I'll talk to you on Thursday.
See you.
Bye.
Thanks.
Don't let me go over. Yell at me. All right.
All right.
Use my button here. That one. Oh yeah, there we go. Stop share. Stop share. No, stop share. Stop share. End.